Something we need to check now is if this matrix lambda is actually invertible. So now we will quickly prove that. To prove that a matrix is invertible, one way is to prove that it's symmetric and positive definite. And to prove that, we need to prove two things. One is that phi transposed times phi is symmetric, because as you can see here, basically we're just modifying the diagonal terms with these two terms. So if this matrix is symmetric, then it means that lambda is symmetric at the end, right? And second, we need to prove that lambda is positive definite. And to do that, we need to go over this sequence. First, we need to prove that our core matrix here, phi transpose times phi, is semi-definite positive, because with that, we can conclude that its eigenvalues are greater or equal than 0. And after that, we need to prove that the eigenvalues of lambda are actually greater than 0. And that will let us conclude that lambda is positive definite. Okay? So I'm assuming here you know the basis of linear algebra, and if you don't know these concepts, please go and take a look to them before continuing with this video. Okay, so let's start with this. How we prove that this matrix is symmetric is actually straightforward. We just need to apply the properties of the transpose, meaning that usually you transpose both matrices and you invert the order, and the transpose applied to the transpose cancels and you end up in this result. So you can see we had one matrix originally here, we transposed it and we ended up in the same one. It means that the matrix is symmetric. Okay, that was easy. Now let's start with this part of the sequence. How we prove that phi transpose times phi is semi-definite positive. In general, to prove that one matrix is semi-definite positive, we need to calculate the dot product of any vector and use this matrix in the middle. It's like to dictate the way we're doing this dot product. If we get a greater or equal 0 result, it means that the matrix is semi-definite positive. And actually, here is easy again, because if we can factor this is exactly as doing this product, and we are multiplying one vector by itself. And when you do that, your result is greater or equal than 0. Okay, one property of matrices, if you prove that it's semi-definite positive, then a direct conclusion is that the eigenvalues of it are greater or equal than 0. So we have accomplished that already. Okay, so let's go for the next one. How we prove that the eigenvalues of lambda are positive. First, let's call this matrix A. The first thing we can note here is that we know that A is semi-definite positive, because here we're just dividing by a positive term. And since this is already SDP, we are not changing that property in the matrix by dividing by sigma squared. The second thing we can note is we are adding this term to the diagonal. And we know that 1 divided by alpha squared is greater than 0. And also, let's assume that lambda is an eigenvalue of A. And you know that this is the typical equation to calculate the eigenvalues and eigenvectors, right? So let's assume that lambda is going to be A's eigenvalue. What we can tell now is what happens if we calculate the eigenvalues of A plus this term here, the identity divided by alpha squared. We need to do again the same equation, our matrix times x, and this x can enter in this product. We have this effect here, and note that we know that A times x is lambda times x, so we can replace this here, and we can again factor by x from the right side, and we end up in this result. So in other words, we're saying that this matrix times x is this vector times x, so this vector is the eigenvalue of this matrix. So with that, we know that lambda was greater or equal than 0. Because A is semi-definite positive, right? And since 1 divided by alpha squared is greater than 0, we're basically adding these two terms, so we end up in a result that is greater than 0. With that, we can conclude that the eigenvalue of this new matrix is also greater than 0. So finally, this can directly take us to what we want, to prove that lambda is positive definite. So that's why our matrix lambda is invertible.